everyone. If you remember last time we proved it was theorem 5.6, and what it said is that anytime if you have a polynomial, the corresponding Galois groups acts as a permutation group of the set of roots, right? So it's something like you could essentially say it this way, if you interpret this correctly, that gamma of f, when any time I have a polynomial, the Galois group of the polynomial is really, technically it's isomorphic to a subgroup of the symmetric group on the set of roots, right? So the group of permutations of the roots. Now, one thing to notice, so this was 5.6, and so let's just say note that this was true for any polynomial. We didn't require that the polynomial be irreducible. So note that 5.6 does not require irreducibility. Now, it turns out that in the case that the polynomial is irreducible, we can say a little bit more. So in the case that f is, well, let's say f in k bracket x is irreducible, then from, this was corollary 2.9, so then by corollary 2.9, for each, say, alpha I and alpha j in the set of roots, there is some sigma in gamma of f such that sigma of alpha I equals alpha j. So anytime you here, so here we are in R, right? R is our collection of roots. All right, so there's an alpha I and there's an alpha j. And then what this is saying, what corollary 2.9 gives us, is that there is a permutation that takes alpha I to alpha j for any choice of alpha I and alpha j. And there's terminology for this. So in this case, we say that gamma of f acts transitively on the set of roots, so on the set capital R. Now, okay, so fine. If we have an irreducible polynomial, then the Galois group acts transitively on the set of roots. On the other hand, so if let's see, I think I need it to be separable, right? I need my polynomial. Yeah, so let's say that I have, let's say, suppose f in k bracket x is separable with degree of f, let's say, equal to n. Now, what does that mean? So the set, since it's a separable polynomial, that means that we don't have multiple roots. So then the set R in sigma consists of exactly n elements. And what I want to do is I'd like to assume that gamma of f acts transitively on R. So let's assume that gamma of f acts transitively on capital R. So let's pick some root alpha. So let's say fix alpha in capital R, and then let's choose anybody that's some other root. So let's let say beta be any root not equal to alpha, right? So just pick any beta. Okay, so because of our assumption of transitivity, we know that there's going to be some element, right, some sigma in gamma f that takes alpha to beta. So let's let sigma in gamma of f be such that sigma of alpha equals beta. So now, if we look at, so I want to look at m sub alpha of beta, that's equal to, so beta is sigma of alpha, so this will be m alpha of sigma of alpha. Right, and then we've seen this already, so I'm just going to do it. So this is sigma of m sub alpha of sigma alpha. That's equal to sigma of m alpha of alpha, which we know is sigma of 0, right? Alpha is a root of m alpha, and so that's equal to 0. Okay, so what does that tell me then? It tells me that m sub alpha has at least n roots. Fine. Okay, so m sub alpha has at least n roots. Okay, so now this tells us, so this implies that the degree of m sub alpha is greater than or equal to n. Now, since m sub alpha has to divide f, right? Alpha is a root of f, which means that the minimal polynomial has to divide the polynomial f. So what do we have then? So we conclude that, okay, so what would the relationship between m alpha and f be if we know that f has degree n, m sub alpha has degree greater than or equal to n, and m sub alpha divides f? Well, it tells us then that f is just a constant multiple of m sub alpha. So we conclude that f is equal to, say, let's say c times m sub alpha. Okay, so what does that tell us here, where c is just some constant in k? So what that tells us is, therefore, f, well, if f is a constant multiple of an irreducible polynomial, then it's got to be irreducible also. So therefore, f is irreducible over k. So what did we show? We showed that if we have an irreducible polynomial, then the Galois group acts transitively on the set of roots. And then with just this added condition that it's separable, right? If we start off with a separable polynomial, and with the knowledge and the assumption that the Galois group acts transitively, we're able to conclude that it's irreducible. So it's almost an if and only if statement, although we had to add this separability in there. Okay. So let's I want to return back to, so let's say so far, right? I want to get back to this connection between polynomials, the fixed fields and subgroups of the automorphism group. So far, given an extension L over K, here's what we talked about this a little while ago. So we have a couple of sets, right? So script G, that's going to be all subgroups of the automorphism group of L. So that's the set of all G such that G is a subgroup of aught L. And then we had script F. That was the set of all M such that M is a subfield of L. And then we had this connection between the two, right? So we go from G to F, right? There's a phi going one way, there's a gamma going the other way, and I think I mentioned this before, that one way to think of Galois theory, or a question that Galois theory wants to answer, is to what extent are these two mappings right here inverses of each other? All right, so we'll say it's something like this: what is required for phi and gamma to be inverses? Well, I mean, when you look at this setup right here, I mean, you should see, I mean, first of all, we know that they're not always inverses, right? There are cases where we have proper inclusion. And so, right, so in fact, here, let me just say that. So in general, we have, G is a subset of gamma phi of G, and let's say, what do I use, M? M is contained in phi gamma of M. That was theorem 5.1, but if L over K is not Galois, then we definitely do not get equality, right? We know that K is not equal to phi gamma of K, right? So that tells us that we will not have inverses in the case that L over K is not Galois. So, I mean, you might say, there's something fishy here. We started off with an extension L over K, but then notice the rest of this does not even mention K. And that's the problem, right? So the problem is that both, G and script F completely ignore the base field K. In particular, right, script F ignores the question of whether L over K is Galois, right? And we know from right here, right, if it's not Galois, then something bad happens. So, what's the solution Well, I mean, the solution is to modify these two sets, right? Right? We want to somehow get k involved, and then I don't know. We may have to mess around with phi and gamma, but always we want this idea that there's this interplay between fields, field extensions, and groups, right? And so that's what we're going to do next. So the solution is to modify script G and script F. So what we're going to do then is we're going to define, first we'll define script G hat. So remember, G hat is the set of subgroups of the automorphism group of L. Now what we want to do is add some mention of K. What we want, right, so it'll be this, the set of all G such that G is a subgroup of the automorphisms of L that fix K. And excuse me. Also, we'll have an F hat. That's going to be the set of all fields, right? So before they were just subfields of M. Now we want subfields that lie in between phi gamma of K and L. Now, this might look a little bit odd right here, but we'll see that we actually need this, okay? So these are going to be subfields of L that lie intermediate to this. And remember, in most cases, we're going to be interested in the case that that our extension is Galois, in which case we'll be able to replace this with capital K. But this is the more general, in the more general setting, this is what we want our script F to look like. Now, so let's say a couple things to note here. So the first one, so just remember that phi gamma of K, that is the fixed field of the Galois group of L over K, right? So this right here, right, we could say it's the fixed field of the Galois group. So that's what's going on right there. And then the second thing, just to point out, so when L over K is Galois, we'll be able to replace phi gamma of K with K. So it'll give us sort of a cleaner statement. Okay, so now the question is, all right, we've modified these sets. Is there still a nice connection between the two via phi and gamma? Okay, so first let's take, so if we take G in script G, okay, what does that mean? It means that G is a subgroup, right? So let's say then G is a subgroup of gamma of L over K, which, by the way, that's just gamma of K. So now, if we use so remember these maps are inclusion reversing. So since phi is inclusion reversing, we have that phi of gamma K is contained in phi of G, and let's remember that phi of G, of course, is contained in L, and so phi of G is one of these M's right here. So therefore, phi of G is an element of script F hat. In other words, if I wanted to have a map from here to here and use the same formula phi, right? At least we've got the codomain correct, right? The codomain makes sense, right? So phi can then be viewed as a function from g hat to f hat. Okay, so now let's see about going in the opposite direction. So also, if we take somebody in script f, so let's call it m. So if m is in script f hat, then what does that mean? It means that m lives in between these two sets right here. So then gamma of m, that's equal to the Galois group of L over m, just by definition. Now, since what, k? Oh, right, yeah, so since k is contained in phi gamma of k, which is contained in m, we have the Galois group of L over M, right, is a subgroup of the Galois group of L over K. If you are if you fix everything in M, then you definitely fix everything in K, right? So that's why we have inclusion in this direction right here. And so gamma of M is an element of, right? It's a subgroup of this guy, so it plays the role of one of these G's right here. So gamma of M is in script G. Okay, so what do we have then? Thus, we have this setup right here, right? A connection between them given by gamma and phi, right? So we have phi going in this direction and gamma going in this direction. And this connection right here, this is called, it's often referred to as the Galois correspondence. What was I about to say? Right, so there's a connection between subgroups of the Galois group and fields that lie intermediate to L and phi gamma of K. Okay, so now we're ready for a theorem. So this is theorem 5.7, and this theorem has a name, right? It's called the fundamental theorem of Galois theory. So with a name like that, it's probably important, right? And there's three parts of this, but it goes like this. It has very minimal assumptions. Let L over K be finite. That's it. All it requires is a finite extension. And then three parts. Part A, phi from script G hat to script F hat is a bijection with inverse gamma, right? So remember I said this to what extent are gamma and and phi inverses. Well, what did we need? We needed to modify our definitions, right? We needed to really modify the domains of the two functions and the corresponding codomains. And then all we require is that L over K is finite. So there's part A. Part B, G is a normal subgroup of gamma of L over K if and only if we have a corresponding normal extension, phi of G over phi gamma, yeah, okay, so yeah, phi of gamma of L over K. So an extension of a couple of fixed fields is normal. So in some sense, it now makes sense. We define this concept of normality of extensions, and now we see that there's a direct connection between normal subgroups and normal extensions. All right, so the terminology makes sense now. And then part C, if G is normal, right, then we can take a quotient, and so then gamma of L over K mod G is isomorphic to the Galois group of this extension right here. So gamma of phi of G over gamma, phi of gamma of L over K. And I don't know why I'm using this sort of clunky notation, right? I mean, this, of course, right here, this is phi gamma of K. And the same thing here. So if you want, you can replace phi gamma of K, or replace this with phi gamma of K. Okay, so there's the statement of the theorem. And we're going to prove this. It's going to take a couple days. So what I'm going to do right now, I'm going to prove part A. And then parts B and C, yeah, I can probably do, yeah, I'll do that in the next lecture. So that'll really be the content of the next lecture. The proof is not overly difficult. So what do we need to do? Well, I want to show that we've got a bijection, that phi is a bijection, so I need to show that it's 1-to-1 and onto. One thing that I want to point out, and we'll use this in a second, but let me just get it out of the way. So we're assuming that we've got a finite extension. So since L over K is finite, what do I need to say? Oh, right, so we know, so we have that the order of the Galois group so we know that this is less than or equal to the degree of the extension. That was theorem 5.5. And so, why do we care about that? That means that whenever we look at a subgroup, an element of gamma hat, it's a finite group. So we can say, and so the order of G is finite for each little g in script G hat. Okay, so let's pick a couple subgroups in G hat. I'm going to call them what? G and H. So let's pick G and H in script G hat, so these are subgroups of the Galois group. And suppose that phi of G equals phi of H. I want to show that phi is 1 to 1, so I need to conclude that G is equal to H. Well then, G is equal to gamma phi of G. And this is from theorem what? 5.4b. Sorry. Theorem 5.4b. Right? All you need is finiteness. If your group is finite. Oh man. Then you get equality right here. Let me just make sure I'm saying that right. Sorry, my allergies are kicking in right now, and the chalk dust is definitely not helping. 5.4. Whoops. Right. So yeah, anytime when you have a finite group, when our group is finite, then you get equality right here. So that's what 5.4b says. Now, we've assumed that phi of G is equal to phi of H, so I can substitute phi of G for phi of H for phi of G, and then we can apply the theorem again. This is equal to H. So once again, that's theorem 5.4b. Well that was nice. So therefore, phi is 1 to 1. All right. So now I need to say a little bit. Okay, so I want to show onto, which means I need to pick something in an F hat and find somebody in the domain that gets mapped to it. But a little bit of lead in before I actually do that. So it goes like this. So by theorem, and it's 6.4c. By theorem 6.4 is it? No, it's not 6. That's a typo in my notes. Let me fix that. That should be 5.4. Okay, so by theorem 5.4c, L over phi of G is Galois for each G in each G in script G, right? So each subgroup, and that's just finiteness once again. Fine. Okay, so in particular, if I look at if G equals gamma L over K, which is equal to gamma of K, then L over phi gamma of K is Galois. Okay, so now I'm going to leave that up. So this part right here, I'm going to use in 1 second. Okay, so this is pretty fun, but I just got to get all the pieces right for the punchline. So let's pick M in script f hat. So then we have this setup right here. So phi gamma of k is contained in M, which is contained in L. That's just what it means to live in script F. And we know that this extension is Galois, which means that it's both normal and separable. All right, so this extension right here is normal and separable. All right, so that's directly from there. Okay, fine. So this is so bicorollary (3.4) L over M is normal. By theorem 4.1, L over M is separable. Right? When you have normal and separable, then when this extension right here is normal and separable, then the front end is both normal and separable. And then we also know, so since we know that just by the Tower law, L over M has finite degree, right? So it's less than infinity. We have that, well, let's see, what do we have? L over M is a finite, normal, separable extension, which means that it's Galois. So we have that L over M is Galois. Okay, well now we know that, so this is now by theorem, 5.5, we know that phi gamma of M is equal to M, and so what does that tell us? It tells us that phi is onto, right? We chose somebody in the codomain, and we found somebody in the domain, namely gamma of M, so that that gives us the output of M. And so phi is onto. Okay. I mean, that kind of sneaks up on you, but that completes the proof, right? We've got a bijection, right? And gamma is the inverse, right? Phi gamma of M equals M, and gamma phi of a group equals the group of the subgroup. Okay, so we'll stop here, and then we'll prove the rest of the theorem on the next time. All right, see ya.